morning to all of you. Jai Hind. My name is Arun Kumar Maurya, Assistant Professor in the Department of Electrical and Electronics Engineering at AKGEC, Ghaziabad. In the Power System Lecture Series, the new topic is performance of lines in the power system network. So these are the contents. What is the classification of transmission line and their performance parameters, and there are three types of transmission line. First one is short, second one is medium, and the third one is long transmission line. So in this lecture I will discuss about the short transmission line and its equivalent circuit and their phasor diagram for short transmission line. So as I have discussed, according to the length of the line, the transmission lines are classified as: first one is short transmission line, second one is medium transmission line, and the third one is long transmission line. In the short transmission line, a transmission line having a length of fewer than 80 kilometers. So every line in the short, medium, and long, the range, the length, the range, and the voltage level is defined for every of the lines. So these are the responsible parameters to choose the suitable line. So in the short transmission line, the length is 80 kilometer. So this is considered as a short transmission line, while the length is less or equivalent to 80 kilometer or 50 miles. The operating voltage of the line is less than 20 kilovolt. That is 20 kilovolt. So this question may be asked for the MCQ while we go for the competitive examinations. The question may be asked like that: what is the operating voltage of the short transmission line? Option A, B, C, D, 20, 30, 70, 40, like that. So which is nearer to the 20 kilovolt. Somehow in some books the operating voltage of the line is taken as 22 kilovolt. In some books there is a mention of 18 kilovolt. So this is not a problem. You will around a voltage for which is close to 20 kilovolt. So 20 kilovolt is the operating voltage for the short transmission line, and the length is 80 kilometer. For the AKTU examination point of view, they may ask a question: what is the length of and the operating voltage of the short transmission line? So these are the some points which are very important for scoring. So these are points to be considered and understandable while we use these type of things. In the other point, the capacitance of the line is neglected due to the small length and low operating voltage. So it's a phenomena, and it's a thing that capacitance of the line is neglected due to the small length and the low operating voltage. Therefore, the performance of a short transmission line is only depending upon the resistance and the inductance. In the circuit, we will see only the resistive and the inductance, and we will neglect and we will remove the capacitance while we use the short transmission line. The representation of a short transmission line is done using the series connected resistance and the inductance. This point is important while we use the phasor diagram of short transmission line. The representation of a short transmission line is done only using the series connected resistance and the inductance. In the second case, medium transition line, a transition line having a length between 218 to 20 240 kilometer. Uh, the this type of transition line is considered under medium transition line. The length in the range of 80 to 240 kilometer, and it's generally the operating voltage of a medium transition line is 20 kilovolt to 100 kilovolt. So this is important operating voltage range. In a medium transition line, the charging current is present, and we cannot neglect it like in a short transition system which we have seen in a previous slide. Therefore, we have to consider the capacitance due to the sufficient length and operating voltage. So in the medium transition line, we will not neglect the capacitance due to the sufficient length and the operating voltage level. So the medium transition line is represented by a resistance, inductance, and also capacitance. There are three methods to represent the medium transition line: nominal T, nominal pi, and the hybrid method. A transmission line, I am considering the long transmission line, a transmission line having a length of more than 240 kilometer. So 240 kilometer range is a big range as compared to the other short and medium line. A transmission line having a length of more than 240 kilometer is considered as a long transmission line, and the operating voltage for it around 100 kilovolt. So these are the two important range and the terms while we use the long transmission line. The question may be asked, what is the operating voltage and range of long transmission line in the power system network? The model of a long transmission line is a uniformly distributed model over the entire length of a line. So it's an important point, uniform distributed model. We cannot consider a lumped model like a short and medium transmission line. Okay. Line constants are uniformly distributed over the entire range of length of a line, and the resistance and inductance are in series of an element. So we will see the circuit diagram, phasor diagram, and the derivation of the short, medium, and the long transmission line. Here I will discuss in the lecture series. I will show you the short transmission line, phasor diagram, circuit diagram, and the derivation. So to analyze the performance parameters, so these are some parameters to show the analysis of any line that is short, medium, and the long. So we have to consider the most important some performance parameters like voltage regulation and the transmission efficiency. These two terms are common for the electrical engineers. We already know, and when we are in the first year and the second year, we would have a detailed discussion about the voltage regulation and the transmission efficiency in the electrical machine, basic electrical engineering, and the other subjects as well. So these two terms are important for the performance parameters to see in the transmission lines. With the help of these parameters, we may see the derivation of the short, medium, and long transmission line. So if we talk about the voltage regulation, due to the line parameters, resistance, capacitance, and inductance, a current carrying transmission line has a voltage drop. Therefore, the receiving end voltage is less than the sending end voltage. This is simple thing. A current transmission line has a voltage drop, so the receiving end voltage is less than the sending end voltage. The difference between sending end voltage and the receiving end voltage expressed as a percentage of receiving end voltage is called the voltage regulation. Mathematically and the formulation point of view, the percentage voltage regulation of the line is expressed as the equation voltage regulation Vs minus Vr divided by Vr into 100, and this is the mod Vs minus Vr divided by Vr. So in this, Vs is higher and Vr receiving and voltage is low as compared to the Vs. And second parameter is transmission efficiency. Due to the impedance of a transmission line, some amount of loss occurs. This causes some amount of power at the receiving end is less than the power input at the receiving end. This is transmission efficiency. The transmission efficiency is defined as ratio of receiving end power to the sending end power, and mathematically it is to be expressed as transmission efficiency equal to receiving end power divided by sending end power into 100. So this is transmission efficiency, which is represented by eta t. Eta t equal to Vr IR cos phi divided by Vs Is cos phi. So Vr is receiving end voltage into what is power? Power is Vi cos phi. This is active power, real power, true power. So P equal to Vi cos phi. Here is a receiving end power. So receiving end voltage is Vr and receiving end current is IR into cos of power factor angle, that is phi r, divided by sending end power. So sending end voltage Vs multiplied by sending end current, that is Is, into cos phi, cos and angle of voltage and cos phi s. So this is the transmission efficiency formula. Eta t equal to Vr IR cos phi r divided by Vs Is cos phi s into 100. This is the formula of transmission efficiency. In short question, these things may be asked in the examination point of view. In the circuit analysis and the representation of a circuit, short transition line, the equivalent circuit is shown here. So this is a single phase line of a short transition line circuit. So this is source, and this is R1 X1. So this is total Z impedance of R and X. So this is the let's say sending side, sending and voltage, and here it's a load. This is receiving side, this is sending side, and this is receiving side or a load side. R1 X1 and this is R2 X2. This is receiving end and this is sending end, and which is equivalent circuit modeled as this is source and the input or a sending end voltage is Vs and the sending end current is Is, that is I, and Rx is the impedance, and this is the load or receiving end voltage and the current, that is IR current, and VR is receiving end voltage. So in a short transmission line, I have discussed in the previous slides that a capacitance will be neglected, will not be considered due to the low length and the low operating voltage in a short transmission line. So use only inductance and a capacitance. Sorry, inductance and a inductance. Capacitance would not be considered. It will be neglected. So the shunt capacitance and the shunt conductance are neglected. Hence, sending end current and receiving end current is same. That is IS equal to IR. That is what? This is source current. So if we use the law, KVL KCL law, so here we use the KVL law. VS equal to VR plus IR, that is IR plus JX. So VS equal to VR plus IR and total impedance Z, which is R plus JX. So VS equal to VR plus IR total Z, which is R plus JX. Shunt capacitance are neglected. So this is VR and IR into impedance. What is this? This is IR and this is total impedance. And we know that the source current is same as like that the receiving or the load side current. IS equal to IR, which is I. So in a 4-terminal passive network, the sending end voltage and sending end current are related with the receiving end current and the voltage by a following pair of equations. So we have already known the two-port network in the network analysis and synthesis subject, how the parameters are calculated. So in this formulation, in the short transmission line, the ABCD parameter of a line is given as VS equal to AVR plus VIR and IS equal to CVR plus DIR. On a comparing of the results, A equal to 1, B equal to Z, C equal to 0 and the D equal to 1. So this is the phasor diagram of short transmission line. This diagram is already discussed. This is sending end voltage, this is source, R plus JX, that is Z, and this is receiving end voltage, that is VR, and I and IR, IS is same because they are all are in series, and the source current, that is IS, IR and I is same. So this is the phasor diagram of short transmission line. That is VR is taken as a reference, phi is the lagging, so IR is here, and after that IR into R while we seeing the equation. So IR into XL and the VS, total sending and voltage VS. So this is a very simple phasor diagram of short transmission line. We have easily and we have a comprehensive analysis of different types of lagging and leading factors while we considering the phasor diagram of electrical networks. by seeing this, network, this is a simple network, and the phasor diagram is like that. So this part is for short transition line. In the other lectures, we will see the medium and the long transition line, their performance parameters, their voltage regulation, and the transition efficiency formulations, and the ABCD parameters of the medium and the long transition lines, and their correspondingly phasor diagram and its equivalent circuits.